Now, before we get into anything at all, I want to ask you to do me a quick favor.
Oh, starting with homework right out of the gate.
Just a tiny bit. I want you to take a second and look around the room you're sitting in right now.
Okay.
The coffee cup sitting next to your hand. Or even just hold up your own hand and look at it.
All very solid, reliable objects.
Right. But here is the thing. Everything you see, everything you can touch, everything you interact with on a daily basis, it's all just the Generation 1 version of the universe.
Generation 1.
Yeah.
It is remarkably stable, beautifully organized, and when you get right down to it, incredibly basic.
Basic. Yeah, that's the perfect word for it. But here is the cosmic secret we're unpacking today. The stuff that makes up you and me, this ordinary matter of our everyday lives, it's just the tip of the iceberg.
Just a fraction of what's actually out there.
Exactly.
They blink into existence, heavy and chaotic, and then almost instantly, they decay. They vanish.
But they don't just vanish into nothingness.
No, they don't.
Yeah.
And that is the crux of the matter. They transition, they break down, they transform. The universe doesn't do magic tricks, it does accounting.
Accounting.
Welcome to the Deep Dive. I'm Satosha.
And I'm Satoshi. How exactly the universe recycles these heavy, exotic particles back into the stable, boring, everyday stuff that makes up you and me.
The Generation 1 stuff.
Right. We're specifically looking at the peculiar, almost alchemical transitions of these exotic particles. We're talking about heavy particles with incredibly sci-fi sounding names.
Name conventions are wonderful.
They really are. We've got leptons called the muon and the tau, and quarks called the charm and the strange.
I will admit, it sounds incredibly intimidating when you list off names like muon and strange quark.
It sounds like you need a PhD just to say the words.
It does. It sounds like high-level particle physics that requires a chalkboard full of Greek letters. But if we really look at the mechanisms outlined in the research, it operates with a surprising amount of mundane logic.
Mundane logic. I like that.
You can think of it as a cosmic recycling center. It's managed by some very strict, slightly quirky rules, and it relentlessly breaks down the heavy, unusable material into the stable building blocks of our reality.
A cosmic recycling center. That's exactly what we're touring today. And I want to make a rock-solid promise to you right now as you're listening.
We are holding ourselves to this.
We are going to explore this entire cosmic recycling process, this whole wild world of particle transmutations without speaking a single mathematical equation.
Not one.
No algebra, no calculus, no complex formulas. We are leaving the equations on the chalkboard. Instead, we're going to rely on relatable, everyday examples. We're going to use analogies that actually make sense to us.
We can absolutely understand the how and the why without getting bogged down in the computation.
Yeah.
The underlying architecture of the universe is surprisingly elegant, even when it's being completely ruthless about breaking things down.
Okay, so real quick before we jump into the deep end, if you are getting value out of this show, we request you to check us out on Fountain FM. It's a value-for-value player where you actually get paid for listening without advertisements blocking your experience.
It's a great platform.
And of course, you can listen to us on Spotify, Apple Podcasts, or YouTube Music for free, or wherever you get your audio fix. As for videos, we still need to hit our goal of 1,000 subs on YouTube to start using the Mosaic AI video editor.
Mosaic is truly a game changer for small creative like us.
It really is. We can feed it a YouTube link, and it creates beautiful AI cinematic captions, infographics, and a whole lot more we're still discovering in our capability tests.
So hit that subscribe button.
We can't be more thankful that you all are as fascinated by these deep dives as we are.
The key to this vote of confidence is the research we share on our website.
Exactly. No login needed, no cookies, no trackers, and absolutely no advertisements. So please, if you want to dig deeper into the numbers, check the link in the descriptions.
Because today is a big one.
Huge. Let's unpack this. To understand the recycling process, we first need to understand the material being recycled, right?
Naturally.
Let's start with the blueprint of reality. The research calls it the standard model. What are we actually looking at when we talk about the building blocks of matter?
So the research defines the standard model as the most robust theoretical architecture we have for describing the fundamental constituents of matter.
The bottom floor of reality.
Exactly.
Yeah.
It organizes the foundational building blocks of the universe, excluding gravity, which is its own separate, very complicated issue, into 12 fundamental matter particles.
12. Just 12.
Just 12. In physics, we call these matter particles fermions.
Fermions, that's a term that pops up a lot in these papers. Where does that word even come from?
It's named after Enrico Fermi. Yeah, one of the great pioneers of quantum mechanics. Essentially, if a particle takes up space, if it constitutes stuff rather than just transmitting a force, it is a fermion.
Got it. So we have 12 fermions, 12 fundamental building blocks. That's it. The whole universe, every star, every galaxy, every slice of pizza you've ever eaten boils down to just 12 pieces.
Precisely. And the standard model groups these 12 fermions into two main camps. On one side, you have the quarks.
Okay, quarks.
On the other side, you have the leptons. But it doesn't stop there. Nature, for reasons we are still trying to fully comprehend, organizes these quarks and leptons into three distinct generations.
This generational structure is where it gets absolutely fascinating to me. I was looking at this table in the research, and the way these generations are structured, like a family where every new generation is just a much heavier, wildly unstable, chaotic replica of the last one.
A very apt description.
Let's break this down for you. Generation 1. Think of this as the sensible foundational generation.
This is the generation you are intimately familiar with, even if you don't know the names. Generation 1 includes the up quark and the down quark.
Up and down.
Right. It also includes the electron, which is a lepton, and its ghost-like partner, the electron neutrino.
The up quark, the down quark, and the electron. If you've ever taken a high school chemistry class, you know that protons and neutrons make up the nucleus of an atom, and electrons orbit around them.
Yes, the classic planetary model.
Exactly. Well, protons and neutrons aren't fundamental. They're actually made of up and down quarks bundled together. So Generation 1 is literally us. It's the desk. It's the planet Earth. It is the stable, everyday stuff.
It's what the research calls ordinary baryonic matter. And because it is the lightest generation, it is stable.
It's grounded.
Exactly.
Yeah.
It doesn't decay into anything else because there is nothing lighter for it to decay into.
Right.
It has reached the ground floor of the universe's energy elevator.
But then the universe decided it needed sequels. It wasn't happy with just the ground floor. We get Generation 2 and Generation 3, the heavy hitters, the chaotic rock stars of the particle world.
Indeed. Generation 2 introduces the charm quark and the strange quark.
Great names.
Fantastic names. And for the leptons, it gives us the muon, which is essentially a heavy electron, and the muon neutrino.
Okay, so that's Generation 2.
Then we move to Generation 3, which is heavier still. Here, we find the top quark and the bottom quark, along with the tau lepton, an even heavier, more unstable version of the electron and the tau neutrino.
Charm, strange, top, bottom, muon, tau. These guys are the ghosts we mentioned earlier. The research points out that these Generation 2 and 3 particles have significantly higher masses and incredibly short lifetimes.
Incredibly short. Fractions of a fraction of a second.
Right. They just do not stick around. They are created in extreme high-energy environments like inside exploding stars, or when cosmic rays smash into our atmosphere, or down in giant particle accelerators, and then they immediately fall apart.
They essentially act as heavier replicas of the Generation 1 particles. A muon has the exact same electric charge as an electron.
It does the same job.
It does. It responds to the exact same forces. Structurally, it is an electron's heavier sibling. But because it has so much more mass, it is inherently unstable. In the universe, mass is energy, and high-energy states always seek a lower energy state.
Which brings up a massive question for me. I'm looking at the data, and if a muon is just a heavy electron and a charm quark is just a heavy up quark, why are they heavy?
$1 million question.
Seriously, where does this extra mass actually come from? If they are fundamentally the same type of particle, what makes a top quark tens of thousands of times heavier than an up quark?
The research points straight to something called the Higgs field.
Ah, the famous Higgs field.
Yes. The mass hierarchy within these generations is dictated entirely by how strongly they interact with the Higgs field. This field permeates the entire universe. It is everywhere, all the time.
I was trying to visualize this, and the best way I can think of the Higgs field is to imagine a massive universe-spanning field of deep, thick mud.
Mud.
Just sticky, dense mud everywhere.
A rather messy analogy, but analytically sound for our purposes. Let's run with the mud.
Okay, so imagine all these particles have to run across this muddy field. Now let's take the Generation 1 particles, your electrons and your up quarks. It's like they're wearing lightweight, slick track shoes.
They'd move very quickly.
Right. They zip right across the mud. They barely interact with it. The mud doesn't stick to them. Because they don't interact much with the mud, which is the Higgs field, they don't pick up a lot of mass. They stay light, nimble, and stable.
Conversely, the Generation 2 particles, like the muon or the charm quark, or walking through that exact same muddy field wearing heavy hiking boots.
Oh, so they're sinking in.
Exactly. The mud sticks to them more, they drag more of the field along with them, they interact more strongly with the Higgs field, and therefore, in the language of physics, they possess a higher mass.
And generation 3, the top quark and the tau.
They are wading through the mud wearing lead boots covered in Velcro.
Oh, wow.
They interact fiercely with the Higgs field, dragging enormous amounts of nud or mass with them. The top quark is so heavy, it's roughly the mass of an entire gold atom, packed into a single, indivisible point.
That is mind-blowing. A single fundamental particle that weighs as much as an entire atom of gold, just because it gets bogged down in this invisible field.
It is astonishing.
But what's really wild is what the research notes about the early universe. If you rewind the clock to a fraction of a second after the Big Bang, the Higgs field hadn't switched on yet. The mud was essentially frozen, or turned off.
That is correct. In those first fleeting moments of the cosmos, the temperature was too high. The Higgs mechanism couldn't operate.
So without the mud, what happens to these particles?
They wouldn't interact with the field at all. They would all be essentially massless, zipping around at the speed of light.
Just flying around freely.
Exactly. And without mass, the generations would essentially look identical. An electron, a muon, and a tau would be indistinguishable from one another. It is the Higgs field that gives them their distinct identities by assigning them different weights.
But wait, do we know why they wear different shoes? Like, why does the top quark get the Velcro lead boots while the up quark gets the track shoes?
That leads us to one of the great outstanding questions in particle physics. The research refers to it as the flavor puzzle.
The flavor puzzle?
Yes. We know that the Higgs field gives them mass, and we know how to measure that mass with incredible precision. But we do not know why the interactions are so wildly different.
We just know that they are.
Right. Why does the top quark interact so fiercely with the Higgs field? Why do their masses span such inexplicable extremes? We simply don't have the fundamental theory that explains the why yet. It is a deeply recognized mystery in the field.
The flavor puzzle, I love that terminology. It makes particle physics sound like a culinary mystery. And speaking of flavor, that brings us right to the heart of what you and I are talking about today.
The actual transmutation.
Exactly. We have this muddy, heavy generation 3 particle, and it's unstable. How do we get it back down to a lightweight generation 1 particle? How does a muon actually become an electron?
To understand that, we have to look beyond the particles themselves and look at the forces of nature.
The rules of the game.
Yes, the interactions that govern how these 12 building blocks communicate with one another and push each other around.
Right. We need to introduce the ultimate alchemist of the universe, the weak force. But first, let's define this term flavor transmutation that pops up all over the research.
It is a vital concept.
Because when I first read it, I admit, my mind went straight to, a strange quark tasting like cherry and a charm quark tasting like blue raspberry.
A common, if slightly absurd, misconception.
Yeah, but when physicists say flavor, they aren't talking about taste, right?
Thankfully, no. In this context, flavor is simply the physics term for the identity of the particle.
Identity, okay.
An up quark is a flavor. A strange quark is a flavor. An electron is a flavor. So flavor transmutation is the literal process of a particle changing its fundamental identity.
A full-on identity shift.
Exactly. It is a muon ceasing to be a muon and turning into an electron. It is a strange quark turning into an up quark.
It's alchemy. It's the old medieval dream of turning lead into gold. But instead of wizards and towers, it's happening constantly on a subatomic level all around us.
It is the closest thing nature has to true alchemy, yes. But what is crucial to understand is that not all forces are capable of this. If we analyze the other fundamental forces mentioned in the research, we find they are remarkably, frustratingly conservative.
Okay, let's contrast them so we can see how weird the weak force really is. We have the electromagnetic force and the strong force. The research describes these two as absolute sticklers for the rules.
This is extremely strict. The electromagnetic force governs how electrically charged particles interact, how electrons repel each other, or how they are magnetically attracted to protons.
Right, the stuff we kind of intuitively understand from playing with magnets.
Exactly. The strong force, on the other hand, is what acts as the nuclear glue. It binds quarks together tightly inside a proton or neutron. But both of these forces conserve flavor absolutely.
Meaning they will never, ever change a particle's identity.
Never. You can bombard a charm quark with the strong force all day long. You can put it inside the most intense nuclear reactor we can conceptualize, and it will remain a charm quark.
No matter what.
No matter what. You can hit a muon with an electromagnetic field of immense blinding power, and it might move faster or spin differently or change direction.
But it's still a muon.
It will still fundamentally be a muon. These forces move things around, they bind things together, they transfer energy, but they do not possess the capacity to change the core identity of the fermion.
Enter the weak force, the universe's designated rule breaker.
The only one.
The research explicitly states that the weak force is the only interaction in the known universe capable of flavor transmutation. It is the sole reason these heavy generation 2 and 3 particles are unstable in the first place.
If the weak force didn't exist, a muon would just sit around being a heavy electron forever.
Exactly. The weak force provides the cosmic escape hatch. It's the singular mechanism by which the heavy, high-energy states decay into the lighter, stable states.
It's the engine of decay.
So how does it actually do it? Forces don't just act like invisible magic wands, right? They don't just point at a particle and say, poof, you're an electron now. They have messengers.
They do. In quantum field theory, every fundamental force is mediated by particles. We call these messenger particles bosons.
Bosons, okay.
For electromagnetism, the messenger is the photon, a particle of light. When two electrons repel each other, they aren't just magically feeling a push.
What are they doing?
They are essentially tossing a photon back and forth between them to communicate that repulsion. For the strong force, the messengers are called gluons. But for the weak force, the messengers are massive vector bosons.
And the research gives us names for these too.
Specifically, the research identifies 3 of them: the W+, the W-, and the Z0 bosons.
The W and Z bosons. And I want to pause here because the history of these things is wild. From the notes we reviewed, physicists knew the weak force had to exist for decades, but they couldn't find the messenger.
They couldn't find the W and Z bosons at all.
Because they are incredibly heavy. Unlike a photon, which has 0 mass, the W and Z bosons are colossal.
Extremely colossal.
Right. Back in the early 1980s, over at CERN in Switzerland, they had to build a massive underground ring just to smash protons and antiprotons together at insane speeds.
A tremendous undertaking.
It was the only way to generate enough raw energy to make these heavy W and Z bosons pop into existence so they could finally prove the weak force worked this way. It took an engineering marvel just to see the alchemist's wand.
And it resulted in a Nobel Prize for Carlo Rubbia and Simon van der Meer. It was a monumental triumph of experimental physics. Now, regarding the specific decays we are focusing on today, the muon, the tau, the charm, and the strange quark transmuting the research classifies these specifically as charged current interactions.
Charged current interactions. Okay, I need you to unpack that term for me, because it sounds like I'm reading a manual for an electrical generator. What does charged mean, and what does current mean in the context of a quark changing its flavor?
It is a historical term, a holdover from early theories, but it remains quite descriptive. The current simply refers to the flow or the process of the fermions interacting.
Okay, the process.
The charge part is the key. It means that the messenger particle mediating the interaction carries an electric charge. In these specific flavor transmutations we are studying, the messenger is always a W boson, either the W+, which carries a positive electric charge, or the W-, which carries a negative electric charge.
And the Z0.
The Z0 boson, as the name implies, is neutral, so it doesn't change the charge, and therefore doesn't change the flavor in the same way.
Okay, let's visualize this charged current thing. A particle comes along, let's say a muon. It's heavy, it's unstable, it wants to decay. It interacts with the weak force by exchanging a W boson. And because the W boson physically carries away an electric charge from the muon, it forces the original particle to change its identity.
That is exactly the mechanism. It is fundamentally an accounting issue. If you take a negatively charged particle and you forcibly remove 1 unit of negative charge from it, what is left behind cannot possibly be the same particle.
It has to be something else.
Its fundamental properties have been altered. It has been transmuted.
So to change your flavor, you have to hand off a W boson. It's the toll you pay to cross the bridge to a lower generation. But here is where the research throws a massive, brain-bending logical puzzle at us.
Yes.
This is the part that had me scratching my head for an hour.
The energy problem. It is a fascinating paradox that goes to the very heart of quantum mechanics.
It's a huge paradox. Okay, so you just said the W boson is massive. We talked about CERN having to build giant colliders just to make one. The research gives the mass it's incredibly heavy, tens of thousands of times heavier than the particles we're talking about decaying.
Yeah.
But the particles doing the decaying, like a muon or a strange quark, are relatively light. So how can a light particle emit a messenger particle that is massively heavier than itself? It doesn't have the mass.
It lacks the fundamental resources.
Exactly. It doesn't have the energy. It's like a bicycle suddenly emitting a fully loaded freight train.
Your scale example is very apt. To put it in economic terms, creating a real permanent W boson requires a vast amount of energy capital. It's like trying to buy a multi-million-dollar mansion.
Okay, a mansion.
But the decaying muon only has the energy equivalent of the Louvre change found in a sofa cushion. The math on the surface simply does not work. Energy must be conserved. That is the most ironclad law in physics. A system cannot output more energy than it contains.
Wait, hold on. But it does happen. Muons do decay. We see it all the time. So how does the universe get around this massive energy deficit? The research introduces this concept of a virtual state, a virtual W boson.
Yes.
And I'm going to be honest, virtual sounds like a massive cop-out. Are you saying the universe just allows it to cheat the laws of physics?
It is not cheating. It is utilizing a loophole embedded deeply in the very foundation of quantum mechanics. Specifically, it relies on the Heisenberg uncertainty principle.
Okay, we promise no mathematical equations, but the Heisenberg uncertainty principle is a concept we can absolutely grasp without the math. Let's think of it like a cosmic bank.
A bank that operates on very strict, yet incredibly brief leniency.
Exactly. So you're the muon, you only have sofa cushion money, but you desperately need a W boson mansion to change your flavor, drop your mass, and decay into a stable state. You go to the cosmic bank
To ask for a loan.
Right. According to Heisenberg, specifically the time-energy uncertainty principle, the universe's bank will actually allow you to borrow a massive astronomical amount of energy out of thin air to create this heavy W boson. It will spot you the millions of dollars you don't have.
But there is a severe catch. The fundamental rule of this cosmic bank is that the more energy you borrow, the faster you must pay it back.
The interest rate is insane.
Beyond insane. The universe audits its books perfectly, but it only audits them periodically.
Right. It's a loan with an aggressively tight repayment schedule. Because the W boson is so incredibly heavy, you are borrowing a huge amount of energy. Therefore, the universe demands you give the energy back in an infinitesimally short fraction of a second. We're talking blink and you missed it, to the trillionth degree.
If you don't pay it back before the auditor checks the books, reality breaks.
Reality breaks. That's terrifying.
This extreme time constraint is why we call it a virtual particle. It does not exist long enough to be observed directly by our detectors. It exists solely in this fleeting, borrowed time window.
It's just a placeholder.
It is a temporary fluctuation in the universe's energy accounting that resolves itself before the overarching laws of energy conservation are technically violated.
So to pay the debt back instantly, the W boson has to immediately decay itself into lighter particles. Let's walk you through a real-world application of this from the research just to make it concrete, because this isn't just happening in a lab at CERN, this is happening everywhere. Let's talk about the beta-minus decay of a neutron.
It is a perfect illustrative example, and one that is fundamentally crucial to our existence.
Yeah, I want to emphasize that. Without beta decay, the sun wouldn't shine. The whole process of stars fusing hydrogen into helium relies on protons turning into neutrons and vice versa. And that relies on this exact process we're about to describe. So how does a neutron decay?
Inside the neutron, which is a composite particle called a baryon, we have 3 quarks, 1 up quark and 2 down quarks.
Up, down, down.
The process begins when one of those down quarks, which is slightly heavier, decides to transmute into a lighter up quark.
So the down quark wants to become an up quark. It goes to the cosmic bank. It says, I need to emit a W- boson to carry away my negative charge so I can become an up quark. The bank says, you don't have the energy for a W-. You're just a tiny quark.
And the down quark says, just spot me, I'll pay it right back.
And the universe allows it. The down quark emits this virtual W- boson and instantly transforms into the up quark.
The interior structure of the baryon has changed.
Yeah.
It now has 2 up quarks and 1 down quark.
Up, up, down.
Yes. The neutron has now officially become a proton.
But wait, the W- boson is now out there holding this massive energy debt. It's on a strict cosmic timer. The auditor is coming. It can't stay a W-. It has to balance the books.
Almost instantaneously, before the universe's accounting department can register a permanent violation of energy conservation, the W- boson decays.
It shatters.
It splits into an electron and an electron antineutrino.
And the electron and the antineutrino are very, very light. They represent the change left over from the original sofa cushion energy the down quark had to begin with.
The massive debt of the W boson's mass is erased because the W boson itself is gone.
The book's balance, energy is conserved overall, and the down quark successfully changed its flavor. It's the ultimate Heisenberg heist.
It is an incredibly elegant solution to a profound physical problem. The virtual particle allows the interaction to occur. It allows the sun to shine and the universe to evolve without violating the overarching macroscopic laws of the universe.
It really is elegant. But wait, you just mentioned the accounting department, and that is a perfect segue. Because while the weak force allows these crazy identity changes and virtual energy loans, it's not the Wild West. You can't just change into whatever you want. The universe doesn't allow a muon to just turn into a slice of pizza.
Far from it. The research outlines several rigorous conservation laws that must be absolutely obeyed during these weak transitions. Nature is, at its core, an immaculate, uncompromising accountant.
It checks every box.
Every single one. Every transition must balance multiple ledgers simultaneously.
Let's go through these ledgers because this tells us the rules of the game. The first ledger is pretty straightforward. Electric charge. The rule is whatever the total electrical charge is before the interaction happens, it has to be exactly the same after.
Correct. The net charge of a closed system cannot change. If we look at the muon decay, this is brilliantly clear. A muon carries a negative electrical charge, traditionally denoted as -1.
Okay, so we start with a -1 on the left side of the ledger.
The muon then emits a W- boson. The W-, as the name implies, carries away that -1 charge. What is left behind is the muon neutrino, which, being a neutrino, has an electrical charge of 0.
So the muon, which is -1, turns into a neutrino, which is 0, plus a W- boson, which is -1. -1 equals 0 plus -1. The math works perfectly. The ledger is balanced.
Precisely. And then, of course, the W- immediately decays into an electron, which is -1, and an electron antineutrino, which is 0.
Oh, I see.
So the final state of the whole process, the neutrino, the electron, and the antineutrino, still has a net charge of -1. Charge is conserved perfectly at every single step of the interaction.
Okay, next ledger. Baryon number. Now, earlier you mentioned a neutron is a baryon. We need to define this. What exactly is a baryon and what is its number?
A baryon is any composite particle made up of 3 quarks. Photons and neutrons are the most famous examples. The research notes that quarks carry a specific property called a baryon number. Each individual quark has a baryon number of 1/3. Therefore, 3 quarks together give a baryon a total number of 1. Leptons, like electrons or muons, have a baryon number of 0. They are completely separate.
And the rule here is so simple. It's basically a VIP club policy. The total baryon number must be conserved, which means a quark can only turn into another quark. It can never, ever turn into a lepton.
It is strictly an exclusive club, because a quark must remain a quark to ensure the baryon number remains constant across the interaction. A strange quark cannot suddenly decide to become an electron. It is absolutely forbidden by the architecture of the Standard Model.
No crossing the velvet rope. Quarks stay quarks, leptons stay leptons. Which leads us to the third ledger, lepton number. This one gets a little more specific. It's not just about staying lepton, it's about deep family loyalty.
Yes. The research details that each generation of leptons has its own specific conserved lepton number. There's an electron lepton number, a muon lepton number, and a tau lepton number.
I was trying to make sense of this, and the best way to picture it is like generational passports. If you are born into the muon family, you carry a muon passport. And traditionally, according to the standard rules the research lays out, these passports are strictly checked at the border. They must be conserved. You can't just throw away your passport.
This means if a muon decays, it cannot simply spawn an electron neutrino. It must produce a muon neutrino to carry away its specific muonness, its muon lepton number.
Let's trace that to make sure I'm getting it. A muon decays. It produces a W boson and a neutrino. Because the original particle was a muon, that resulting neutrino has to be a muon neutrino? It's a non-negotiable family tie?
Correct.
Then the W boson decays into an electron and an electron antineutrino. The electron antineutrino cancels out the lepton number of the new electron, so the net electron lepton number created out of thin air is 0. But the original muon lepton number is safely preserved in that muon neutrino flying away.
It is an intricate, perfectly choreographed dance of conservation. Every single particle produced has a specific accounting purpose.
And there's one more rule in the accounting department, a bit of a weird one. Weak isospin. The research introduces this idea that all these left-handed fermions are grouped into pairs, or doublets.
Yes. Nature organizes these fundamental particles into pairs that interact with each other, specifically via the weak force. The up quark is paired with the down quark. The charm quark is paired with the strange quark. The electron is paired with the electron neutrino.
It's like a buddy system for the subatomic world. And the rule is that these weak transitions, these flavor transmutations, generally happen between members of these specific pairs. If you are an up quark, your primary transition path is to a down quark. You're in a doublet together.
They are essentially two sides of the same coin when viewed through the lens of the weak interaction. The W boson simply flips the coin from one side to the other.
So we've got the players, we've got the rules, we've got the cosmic bank loans, and we know about the ledgers. Now it is time for the ultimate comparison. The core question posed by the stack of research, the whole reason we decided to do this deep dive today.
A big question.
Are the decays of the heavy leptons, the muon and tau, and the decays of the heavy quarks, the charm and strange, are they happening in the same way?
It is a profound question. It might seem like a technicality, but it gets to the very heart of whether the universe operates on universal principles or if it has fragmented, specialized rules for different types of matter.
Exactly. And the answer, as with everything in particle physics we've discussed today, is yes, but with a whole lot of nuance. Let's look at the yes factors first. What are the shared mechanisms? How are these decays exactly the same?
First and foremost, they are entirely reliant on the weak force. Whether you are a tau lepton spinning in a void or a charm quark trapped in a particle collider, the strong and electromagnetic forces cannot help you decay. You are completely 100% dependent on the weak interaction to change your state.
Right. They both use the exact same cosmic alchemist. Second, they both involve that change in electric charge we talked about earlier. They both have to emit or absorb a W boson to make the transition happen. The mechanism is identical.
Furthermore, they both follow the principle of generational descent. They are heavy, high-energy particles shedding mass and energy to become lighter, more stable particles from a lower generation. It is a universal drive towards stability. The universe wants to reach the ground floor.
And visually, if we look at the math, or rather the diagrams physicists use instead of math, the Feynman diagrams, the research notes that fundamentally they look completely identical.
If you strip away the specific labels, if you erase the word muon and strange quark, the architecture of the interaction is identical. You have a single line representing the incoming particle. That line hits a point, a vertex, emits a wavy line representing the W boson, and continues as a different particle line. A muon emitting a W boson looks structurally identical to a strange quark emitting a W boson.
So on a macroscopic architectural level, they are absolutely happening in the same way, but the devil is in the details. Let's look at the nuance factors, the structural differences between how leptons decay and how quarks decay, because they are not perfectly identical.
The differences arise from the specific inherent properties of quarks versus leptons. They live in very different social structures, so to speak.
The first big difference is what we just talked about a minute ago, family loyalty. Leptons are fiercely loyal to their generation.
Indeed. As we establish, a muon must turn into a muon neutrino. It stays within its family doublet. It does not jump generations directly. The electron that we ultimately see in a muon decay detector does not come from the muon itself. It is a secondary product, born later from the decay of the intermediary W boson.
The muon essentially just hands off its negative charge to the W boson and retires quietly as a neutrino. But quarks, I'm reading this right, quarks are rule breakers. They're allowed to jump generations directly.
Yes, a strange quark, which is a generation 2 particle, can transition directly into an up quark, which is a generation 1 particle.
Wait, I'm trying to picture this. Why doesn't the strange quark just turn into a strange neutrino and let the W boson handle the rest exactly like the muon did? Why does it cross the generational boundary?
Because, quite simply, strange neutrinos do not exist.
Oh.
Quarks do not have corresponding neutrino partners the way leptons do. Their doublets are constructed differently. The strained quark is paired with the charm quark. Therefore, to decay into a significantly lighter, more stable state, the strange quark has no choice but to cross generational lines. It bypasses the strict family loyalty we see in leptons. It jumps the fence.
So quarks can hop the fence between generation 2 and generation 1 directly. That's a huge difference. And there's another massive difference, maybe the most important one. The research calls it color confinement. But when I was reading the explanation, I kept thinking of quarks as extreme introverts who have a terrible roommate situation.
A very apt, if highly anthropomorphized description. Quarks possess a property known as color charge. Now let's be very clear. It has absolutely nothing to do with visual colors like red or blue. Quarks are smaller than the wavelength of visible light. They don't have visual color.
Right, physicists just ran out of names for things. They use up spin and flavor and charge, so they just started using colors to label a new property?
Exactly. It is simply a naming convention for the charge of the strong force. But the fundamental unbreakable rule of color charge is that it must always be neutral in any observable particle in the universe. A single, isolated quark carries a net color charge. Therefore, the universe strictly forbids a single quark from existing in isolation. It must always be bound together with other quarks to form a color-neutral composite particle.
Which means they refuse to be seen alone. They always have to bring roommates to balance their color out. If a quark tries to leave, the strong force just pulls it right back in or creates new quarks out of the energy of the attempt. So you can have a baryon, which is three quarks, like a proton, or you can have a meson, which the research defines as a quark and an antiquark paired together, but you can never have just one quark.
So when a strange quark undergoes a weak decay and turns into an up quark, it is not happening in a clean vacuum. That strange quark is bound tightly to other quarks by the strong force. When it transmutes, it drags those other quarks along for the ride. The initial composite particle, say a kaon, which is a type of meson, transforms into a completely different composite particle like a pion, or sometimes shatters into multiple new composite particles.
It's a mess. A strange quark decay involves a whole neighborhood of other particles reacting to the sudden change in identity and mass. It's a chaotic event. But leptons don't have color charge. They don't feel the strong force at all.
Leptons are solitary. A muon does not need roommates. It does not need to be color neutral. It exists on its own, it decays on its own in empty space, and its resulting products fly off on their own perfectly clean trajectories. It does not have to deal with the complex, messy, explosive physics of color confinement.
So are they the same way? Yes, the engine driving the change, the weak force, and the W boson is exactly the same. But the vehicle being driven, a solitary, independent lepton versus a clumped-up, roommate-bound quark, reacts to the journey very differently.
A very precise synthesis of the data. The underlying engine is the weak force, but the resulting phenomenology, what we actually see in our detectors, differs wildly based on the structural nature of the particle.
Which brings us to a really fascinating layer of the research, because as we look deeper at the weak force engine itself, we find out it has some incredibly weird quirks. Let's talk about the weak force's handshake. The research introduces a term, chirality.
Virality is one of the most profound and somewhat unsettling discoveries in 20th century physics. It reveals that the universe, at its most fundamental level, is not perfectly symmetrical. It literally has a handedness preference.
What does that mean practically? I mean, I know what being left-handed or right-handed means for a person, but for a fundamental force, how does a force have hands?
Particles also have an intrinsic property that physicists classify as left-handed or right-handed. It is based on the relationship between how the particle spins and the direction of its momentum.
Okay, I'm trying to visualize this. Imagine throwing a football. If you throw a perfect spiral, the ball is spinning on an axis as it moves forward.
A perfect analogy. If the football is spinning counterclockwise relative to the direction it is flying, we call that left-handed. If it is spinning clockwise, we call that right-handed.
Okay, so particles are like tiny footballs flying through space, spinning either left-handed or right-handed. What the research confirms is that the weak force are universal alchemists. The only thing that can change flavors is exclusively biased. It only catches the left-handed footballs. It only interacts with left-handed fermions.
Completely. If a right-handed particle, a clockwise spinning football, approaches a W boson, the W boson will not interact with it. The weak force is entirely blind to right-handed particles. This phenomenon is known as parity violation. Electromagnetism doesn't care, it interacts with left and right equally. Gravity doesn't care. But the weak force, the mechanism of decay and transmutation, is fundamentally asymmetrical. The universe literally prefers the left hand when it comes to decay.
That is wild to me. It's like finding out gravity only works on Tuesdays, or that magnets only work if you're facing north. It's such a specific, arbitrary seeming rule built into the very fabric of reality. But within that rule, within the left-handed interactions, there is a beautiful consistency. The research highlights something called weak universality. I found this mind-blowing.
It is the great unifying principle of the weak interaction. It brings order to the chaos of the generations.
So the W boson has to facilitate decays for tiny little muons, and it also has to facilitate decays for massive, lumbering top quarks. You would think it would treat them differently, right? Like you would need a stronger force to move a heavier object. But weak universality says no.
Exactly. The weak charge, the fundamental strength of the connection between the particle and the W boson, is identical across all generations and all particle types. The research states that the W boson gives the exact same handshake with the exact same strength to a muon as it does to a top quark, or a strange quark, or a tau lepton. The core interaction strength does not change.
But wait, if the handshake is exactly the same, why do some decays happen in a fraction of a microsecond and others happen much, much slower? Why aren't all particles decaying at the exact same speed if the force pulling the trigger is universal?
That is where the environment and the structure of the particles come into play. The speed or probability of a decay depends on two main factors. First, what we call the phase space available. This is a physics term for the mass differences between the parent particle and the daughter particles. If there is a massive difference in weight, a huge drop in energy, the decay happens incredibly rapidly. It has a lot of room to decay.
It's like a steep hill. A ball rolls down a steep hill much faster than a gentle slope.
Precisely. The top quark has a massive hill to roll down, so it decays almost instantly. The second factor, especially relevant for quarks jumping generations, involves mixing matrices. The most prominent one in the research is the CKM matrix, named after Kabibo, Kobayashi, and Maskawa.
The CKM matrix. Okay, break that down for me, because that sounds like heavy math again.
Think of it as a set of probabilities governing how much quarks are allowed to mix across generations.
Ah, I get it. Think of it as a cosmic penalty for jumping family lines. A bureaucracy. Because the strange quark is hopping the fence from generation 2 to generation 1, the universe says, okay, you can do this, but I'm going to charge you a fee. You have to fill out the CKM paperwork. It makes the transition less probable and therefore slower than if you stayed in your lane.
Exactly. The core handshake of the weak force is the same, but the bureaucracy of the jump slows down the overall rate. The universal mechanism is hindered by the specific identity of the quark involved.
Okay, we need to talk about the twist.
Yeah.
Because everything we've talked about so far, all these strict accounting rules, especially the lepton number conservation, the family loyalty, the fact that a muon must make a muon neutrino there is a rebellion happening, and it's being led by the ghosts, the neutrinos.
The neutrino rebellion. The discovery of neutrino oscillations completely upended our understanding of those rigid generational rules. It is arguably one of the most important physics discoveries of the last 50 years.
We need to spend some real time on this because it's a fantastic story. The research lays it out clearly. For decades, the standard model assumed neutrinos were completely massless. They were the ultimate ghosts. They zipped through the universe at the speed of light, never interacting with anything, never changing. A muon neutrino was a muon neutrino forever. It carried its generational passport and never altered it.
That was the assumption. But physics is driven by observation, not just assumption. And the observation that broke this assumption started with the sun. It was called the solar neutrino problem.
Right, back in the 1960s, we knew the sun was powered by nuclear fusion, and that fusion process, specifically that beta decay we talked about earlier, produces a massive, unfathomable amount of electron neutrinos. They stream out of the sun and pass right through the Earth. Trillions of them are passing through your body right now.
So a scientist named Ray Davis decided to try and catch them. He built a massive tank deep underground in the Homestake gold mine in South Dakota. He filled it with 100,000 gallons of perchloroethylene, essentially dry cleaning fluid.
Dry cleaning fluid.
Yes. The theory was that very, very rarely, a solar electron neutrino would hit a chlorine atom in the fluid and turn it into an argon atom. By counting the argon atoms, they could count the neutrinos.
It's a brilliant experiment. But there was a huge problem. When Davis counted the argon atoms, he only found about a third of the neutrinos that the models predicted the sun should be making. 2/3 of the electron neutrinos were just missing.
It was a profound crisis in physics. For decades, people argued. Were the solar models wrong? Was the sun shutting down? Was Davis's experiment flawed?
But the sun wasn't shutting down, and Davis was right. The answer was much weirder. It turns out the electron neutrinos weren't missing. They were in disguise.
Yes. They had changed flavor. This was definitively proven by the Super Kamiokande experiment in Japan in the late 90s.
I've seen pictures of Super K. It looks like a supervillain lair. It's a colossal spherical tank deep inside a mountain filled with 50,000 tons of ultra-pure water and lined with thousands of golden light detectors. What were they looking for?
They were looking for Cherenkov radiation. When a neutrino rarely hits a water molecule, it can create an electron or a muon that moves faster than the speed of light in water. This creates a sort of optical sonic boom, a flash of blue light. And the shape of that flash tells scientists whether it was an electron neutrino or a muon neutrino that hit the water.
And what Super K found was that the electron neutrinos flying from the sun were morphing into muon neutrinos and tau neutrinos while in transit. By the time they reached Earth, the beam was a mix of all three flavors. That's why Davis only saw a third of them. His dry cleaning fluid could only detect electron neutrinos.
But the implications of this are staggering. According to the rules of relativity, if something travels at the speed of light, it does not experience time. If it does not experience time, it cannot change. Therefore, if neutrinos can change flavor if they oscillate, they cannot be traveling at the speed of light.
And if they aren't traveling at the speed of light, they must have mass.
Exactly. The observation of neutrino oscillations prove they must have a tiny, almost imperceptible mass. And because they have mass, as they propagate through space over long distances, a muon neutrino can spontaneously morph into a tau neutrino or an electron neutrino.
They are forging their passports mid-flight. They are breaking the strict Lepton family loyalty rules we just spent 20 minutes defining.
They are indeed. Over short distances, like in the immediate split-second aftermath of a particle decay in an accelerator at CERN, the lepton numbers appear rigidly and strictly conserved. The accounting works. But over vast cosmic spaces, over the distance between the Sun and the Earth, the boundaries between the lepton families blur. They oscillate continually between identities.
This means that lepton flavor isn't perfectly rigidly conserved the way electric charge is. It adds this incredibly beautiful layer of rebellious complexity to the standard model. It means the universe is a little bit more fluid, a little bit more messy than our strictest accounting ledgers wanted us to believe.
It implies that our categories, while deeply useful and structurally sound for most interactions, might have underlying quantum connections we are only just beginning to mathematically understand. The rigid walls between generation 1, 2, and 3 are slightly porous when it comes to the lightest, most ghost-like particles in existence.
Okay, we have covered an immense amount of ground today. We've gone from the desk in your room to the center of the sun to a tank of water inside a Japanese mountain. Let's bring this all together for a grand summary of our deep dive. What does all this mean? We started by looking at this incredible ecosystem of particles. 3 distinct generations of matter. The heavy, unstable, chaotic stuff, and the stable, everyday stuff.
And we identify the weak force as the universe's ultimate transmutation engine. It is the only mechanism capable of breaking down the heavy, high-energy matter from the second and third generations. It relentlessly churns them down, utilizing virtual W bosons, borrowing energy from the cosmic bank and navigating strict conservation ledgers until they reach the stable Generation 1 particles.
The everyday stuff. The stuff making up the coffee cup you looked at when we started. The stability of the atoms in your own body right now is not an accident. It is the end result of this massive, ongoing cosmic recycling program. Everything heavy, everything chaotic eventually finds its way back down to the first generation, thanks to the alchemical handshake of the weak force. Whether you are a solitary lepton flying through space or an introverted quark trapped in a meson, the W boson will eventually find you, take your energy, and leave you as something stable.
We are essentially composed of the cosmic ash of these ancient heavy particle decays. The protons, neutrons, and electrons that make us up are the stable remnants, the final resting state of the weak interaction's relentless work since the Big Bang.
Cosmic ash. That is both slightly morbid and incredibly poetic. We are the leftovers of the universe's wildest parties. As we wrap up this deep dive, I want to leave you with a final provocative thought based on this research we've unpacked today. We just spent a lot of time talking about the neutrino rebellion. We know that these ghostly particles can slowly morph their identities, oscillating from one flavor to another while flying across the cosmos. It tells us that lepton flavor isn't as strictly conserved over immense distances as we once believed. So I want you to ponder this as you go about your day. If the very ghosts of particles, the neutrinos, can slowly drift and change their fundamental identities over time, what does that say about the ultimate long-term stability of the strict categories we use to define the rest of the universe? Are the walls between the generations truly permanent, or are we just looking at them on too short of a timeline?
It is a profound question that pushes at the very boundaries of the standard model and exactly the kind of critical long-term thinking the field of physics requires to make the next great breakthrough.
Thank you so much for joining us on this deep dive into the Cosmic Recycling Center. Keep looking around your room, keep wondering where it all came from, stay curious, and keep questioning the universe around you.
I'm Satosha.
And I'm Satoshi.